Hello everyone, my name is Jimmy and welcome to this week's workshop. This week, I'm going to give a quick introduction to deep learning. So, this is the agenda I planned for this workshop. First of all, I will give a really short introduction to the definition of deep learning. Then, I will talk about the difference between traditional machine learning and deep learning. And then I'll go over and introduce the simplest deep learning model, artificial neural network. And then we'll talk about some interesting facts about deep learning. After that, we'll go to Tensorflow Program. Tensorflow Program is a website that helps beginners to understand deep learning better because they can help have some visualization. And in the end, we're gonna see, I'll briefly go over how a model is trained. Before I start, today I don't plan to go through any real coding because I feel like deep learning is a really big topic and it will be better to have a good basic understanding first and then learn how to code later. Okay, let's take a look at this slide. What is deep learning? The definition of deep learning is basically a learning algorithm that progressively extract high-level features from input and use them to make prediction. I will emphasize this idea in later slides. The reason deep learning becomes so powerful is because how deep it has become. The deep word in deep learning usually means how many hidden layers a model has. The more hidden layer a model has, as the deeper the network is. As this definition says above, if you have a more hidden layer in a model, it can form more complex high-level feature. And usually, with more complex feature, the model can do more powerful things with a better accuracy, like classification tasks or generation tasks. And because of how powerful deep learning is nowadays, it has become one of the most useful things in our daily life. Like many common things we see every day, Alexa, Siri, Google Translate, self-driving car, are all trained by deep learning. Although self-driving car isn't out yet, but yeah. Some people may notice, but most people still have an important question. What is the difference between machine learning and deep learning? As you can see in this picture, deep learning is just a small subset of machine learning. And in the next slide, we'll go over how they are different. So this picture basically tells 90% of difference between the deep learning and traditional machine learning. In a traditional machine learning task, when we have an input, in order to get a good accuracy, good result, usually people have to do the feature extraction first. After that, they put them into a classification model and the model will return the output. However, in a deep learning model, based on how deep the model is, for many times, we can just directly take the input and put them into the model. The model will do the feature extraction and classification together and still return a good or sometimes even better result accuracy. Most people are going to still have a question about how they do feature extraction. I will show how deep learning model make it possible. Before I introduce one of the simplest deep learning model, artificial neural network, I want everyone to have a basic understanding of what a logistic regression model is. Because I think logistic regression has a couple of similarities with artificial neural network. And understanding logistic regression model will certainly help people understand how deep learning model work better, in my opinion. Okay, take a look at this picture. This is a simple logistic regression model. People may ask, what is this? And what are those weird nodes and symbols? I will separate each component out and explain to you. As you can see here, there are multiple input x0, x1, and continue to xn minus 1. They total n input. All those input are connected to an ellipse shaped node. And in the ellipse shaped node, there's a function z equals to w transpose times x plus b, and the sigmoid function after the vertical separate line. Then the output of this ellipse node is the real output. There are 5 weird symbols in this ellipse node, and I will separate each one of them out and tell you what it is. First of all, let's take a look at this function on the left. Z equals to 5 times x plus 1. This is a really simple function that I'm pretty sure everyone will understand. In here, z is the same as z in the ellipse node. It's just the output of a function. And then take a look at w. In this case, w is just 5. It's a way to apply to the input. And some people may ask, the W in the eclipse node has a subscript T on top of it, and that just represents the transpose of W. People may ask, in my simple function example, W is a constant. Why in the logistic regression case, it becomes a matrix in this picture? The reason for that is in modern day machine learning, people always put weight bias input in a matrix or vector to speed up training process. And most of the time, it has more than one input, and each input requires a weight. So it makes sense to have a weight vector and transpose of weight vector in this case, basically distribute the weight to the appropriate input x, like this. For simplicity case, in my simple example, I just have one input, so the W can be a constant. You can still make the one way into a one by one matrix though. Nothing stops you from doing that. Okay, then it's x. X is just the input x. In my example, I only have one input. So if we want to put this into the picture over here, we're just going to have one circle x0 node connected to an eclipse node and nothing else. And then it's the b. B represents bias. In this function, it's +1, which is the same as the thing over here. It's just a constant term. And last but not least, let's talk about this last weird symbol, sigmoid. That's after this vertical bar. Sigmoid is just an activation function. In most cases, the activation function basically transforms the linear function output you get into some nonlinear function output. In sigmoid case, it basically squeezes the output you get between 0 and 1. There are many activation functions, different kind of activation functions. So just know the symbol here stands for type of activation function is good enough. Okay, that's a quick introduction to logistic regression. I hope you understand it. Take a look at the model picture. Remember it, and I will show you in next slides how artificial neural networks are similar to this. Okay, this is the model picture of an artificial neural network. Artificial neural network is one of the a type of deep learning model. There are many different types of deep learning model networks, but in this workshop, I will only introduce this, since this one are the easiest to understand for beginners. Let's first separate the structure of this artificial neural network into 3 parts. For most models, you can see, as in this picture, is the input part, a hidden layer part, and the output part. And in real world case, since we only make it easy, in this case, they only have one hidden layer, but in real world, they can be tens, hundreds, or even thousands of hidden layer. Okay, now let's pay attention to the hidden layer in this picture. Take a look at each node. Notice any similarities with the logistic regression model I showed in last slide? It is all connected by the input layer node. See? All 3 input connected to each of the hidden nodes, see? And it's same as the logistic regression model I showed in last slide, right? As you can see over here, it's all connected. Then each node in hidden layer is like a stack of logistic regression, right? What does logistic regression compute? It computes the output, returns the output, like a final feature from the raw input. So if you apply the same logic here, since for the same input, they'll have different way connected to a different hidden layer node. So like each node in the hidden layer is like a more complex feature from the input layer. Now do you get why the definition of the deep learning is a learning algorithm that progressively extract high-level feature from input and use them to make prediction, right? Of course, if we add more hidden layer, the other hidden layer gonna follow the same behavior, have the same behavior, and it basically means the more hidden layer we have, the ability of the model to compute more complex feature they have. So keep doing that, you will get more complex feature from the input. And now, it's enough introduction to deep learning and the artificial neural network. Before we go over to Tensorflow Program to play around with some simple artificial neural network model, I want to share some interesting fact about the artificial neural network model. Artificial neural network model were inspired by the communication nodes in biological systems. Artificial neural networks work similar to human brain. Each node is like a neuron tool in our brain. We have way connecting the node in artificial neural network, and we have axon to connect neuron in our brain. And human brain neuron activate based on the input, which is the same of how a node gets activated in an artificial neural network. Pretty cool, huh? Okay, so now let's go to the TensorFlow program. And this is the link to the TensorFlow program. And don't worry, I will share the link in the video description, so you can go there in your free time and play around with it. Okay, so now we're in the website. Take a look at it. I'll give you a brief introduction, so I hope you can understand how this website works and can play around with the you can play around with it in a later time. So this website has 4 big components, as you can see, that I want you to pay attention to. The data component over here, the feature model component over here, the output model over here, and the one over here, the tab over here. The tab above here is basically where we control and start the training. And the learning rate, activation, regularization, those are all hyperparameters. Hyperparameters is some simple, in a simple term, it's basically something that we use to control how a model is trained. And now let's take a look at this data component. It's where we select what data we want to use to let model make prediction, because the task of our model is basically try to form a decision boundary between 2 distributions. As you can see, there's a blue distribution and the orange distribution. And you can see there's a different type of distribution we want model to identify. And of course, different distributions have different difficulties. As you can see, this is one of the easiest tasks, because even as human eye, you can see, you can simply form a linear boundary between these two and you get a really good accuracy. And this other part is going to be kind of hard. But anyway, now let's talk about output component. What is the output component? It's basically just how the output we get from like putting input inside this model. So it's nothing special. There's 2 terms I want you to pay attention to. There's a test loss and a training loss. Test loss and training loss is basically how many things you get wrong in either test phase or training phase. For example, if we put 10 value in there and we get 5 wrong, the test loss is 0.5%. Okay, last but not least, let's take a look at this feature model component. This is one of the most important components in this web page. As you can see, we can select how many input we want to provide to the model. You can oversee over here. And of course, the more input you have, the better your model can do, because for given tasks, you can for surely do better if you have more information, right? And now is the hidden layer part. This is the part where we can change the certain hidden layer size, increase or decrease the amount of node, or here we can basically increase or decrease the number of hidden layers. For example, over here, for the first hidden layer, we only have 4 neurons, but we can basically turn to only 3, 2, or even 1. And we can basically decrease or increase the amount of hidden layer size. When we do this, basically we make the model more deep, and if we do this, make it more or less deep. And if we have 0 hidden layer, it becomes a logistic regression. Okay, now the introduction is over. And let me demonstrate how deep learning can help to complete this task. First, I will start with the simplest data set, this part, where we can basically form a linear distribution boundary. Before I apply deep learning training, I will first train using a logistic regression. I'll have 0 hidden layer and see if I can get a good accuracy. As you can see, you reach really good accuracy because how easy the task is. Of course, you can still apply deep learning, but you won't change that much because you already get a good accuracy from logistic regression. So now let's choose a little more complicated task. In this case, I'm going to use this. We will first train using logistic regression and see how we do. As you run, you feel like the model didn't return a good result at all. Nothing is learned. There's no decision boundary between these two distributions whatsoever. Okay, then now let's add one hidden layer and see what's the effect about it. If we run it, we can see the model start getting better. Although it's still not perfect and still has some error over this part, but as you can see, the model already started figuring out that there's something over here that you can use to basically form a decision boundary. What can we do to make this better? We can either increase the hidden layer size or the number of hidden neuron. In this case, I will try hidden neuron first. For example, if I add 2, I run it. As you can see, the model finally learned how to classify these two different distributions, how to form a decision boundary. It's pretty amazing, right? Of course, you can keep adding more hidden layers. I shouldn't change that much because it already reached a good accuracy. As you can see here, you need to have more. As you can see, now we reach a really good accuracy. And now, that's the power of deep learning. In your free time, you can try these two harder tasks, in my opinion. I will not go over how to actually find a module to solve the problem, but because I feel like it's best for you to try it out yourself. Okay, besides solve these two problems, here you can also see how weight and difference input can form complex feature. For example, in this case, the input x1 is just a vertical decision boundary. And x2, you can see it's just a horizontal decision boundary. It's really simple. But with some weight applied to it, it starts to form some weird shape, as you can see over here. Because in here, you can see they both share equal size, but because of different weight, maybe some part shares a little more weight than others. And with that, we can combine to even more complex decision boundaries like here. This is a bad example, sorry, but for example, over here. See over here? Yeah, those are the things that form by basically combining those combining from these two simple input feature. Pretty amazing, right? And that's, if you play more on it, you can for sure have a better understanding how deep learning model can form complex features from some simple feature input. Okay, so now let's head back to how a model gets trained. So basically for the training, we can separate them into 5 main steps usually. The first one is for each weight and biases, we initialize a random value. We run forward propagation. And then we're getting a loss value from forward propagation. Use the loss and do a backward propagation to update each weight and bias. Continue doing this forward propagation and backward propagation until you converge to a really good result, or we reach certain training limit that we set before. I'll go over forward propagation and the backward propagation in the next slides. Now let's see what a forward propagation is. Forward propagation is really simple. You just take an input and put them through the whole network and get an output. The name sounds fancy, but the idea is actually really simple. As you can see over here, you just basically take the input in there, pass it to the hidden neural network, get an output, and that's the concept doing this is just basically a forward propagation. And now let's focus on backward propagation. We first use the output value, remember, and compute the loss between true value. The loss basically means the difference between the real model output and the desired output. For example, if you want your model to output 40, but the model actually output 20, then the difference between these two numbers is lost. There are multiple kinds of loss, and there are also multiple kinds of way to calculating loss. Just remember, you get a loss from doing forward propagation. After that, we use chain rule to update each weight and bias. What is chain rule for non-calculus people? For a simplistic term, chain rule basically tells how a change of one value will affect the other value. Take a look at the model. Each weight and bias over here affect the output, right? You agree. So what chain rule does is basically tell us how a change of this small weight going to affect the output. And we use the information along with the loss to do the value updating to minimize the loss. We keep doing that until we reach the first layer. Basically, we update all the weight and bias once. And then it's one forward and backward propagation cycle. As I said above, continue doing this cycle, and that's it. You successfully trained a deep learning model. And congratulations, you have reached the end of this week's workshop. I hope you learned something from this workshop, and as always, feel free to ask me on Discord if you have any questions. I will also share some interesting YouTube video links in the description that help me learn deep learning. And always, thanks for coming and have a nice day. Bye.